big challenge, which I didn't really talk about from an analytical standpoint. A big challenge of this tool is that you need pretty big samples, right? So Naomi alluded to this issue before. We are still a ways off, in my opinion, from being able to drop that single foraminifera into phosphoric acid and getting a clumped isotope temperature for that single foram. When I was at Caltech, we needed about 10 milligrams, 8 to 10 milligrams of 100% carbonate for a single analysis. And we would run that gas over and over and over in repetition for about 3 hours, right? So the analytical improvements on the instrumentation have made it so our individual measurement is pretty strong. So your reference for this is a single acquisition that we might run to get a C13 and O18 value from that foraminifera. We would run 8 of those repeat acquisitions for a single clumped isotope value. So you know your C13 and O18 really well at the end of it. But essentially what you're doing is you're taking the precision, which gets you part of the way there, the good analytical precision we can get on modern instruments now, and then you're getting the rest of it that we need for, say, plus or minus 2 or 3 degrees C precision. We're getting the rest of that by simply improving our counting statistics, so measuring that same aliquot of gas over and over and over to get a good measurement. And then you would typically take and make 2, 3, 4 replicate analyses of that sample for an end reported temperature on something. So if you need 8 to 10 milligrams for a single analysis, that's something like 40 milligrams for an end well-reproduced sample. So it certainly takes certain things off the table. So not surprisingly, people are working really hard to figure out ways to move to smaller sample sizes. And this has been coming from software changes. So basically, the group at ETH has been exploring basically exploiting instrument stability. We have extremely stable instruments these days and saying, well, instead of taking your dual in the machine and running reference, sample, you end up losing a lot of gas through the process of that. If you can sit on your sample side for a while and just measure, and then switch over to your reference side and just measure, you can get away with a lot less gas. But you make the assumption that your instrument is stable enough that once you've moved over to the reference gas, your conditions, say in the room or in terms of what will affect your instrument stability, haven't changed enough to matter for the measurement and introduce some kind of bias. So people are playing with that. Those of you who have done work with forams, typically you're looking at some kind of micro volume. You've bypassed the bellows completely. So there are people who are playing with similar ideas of macro micro volumes. So something bigger than the standard cold finger that you would use, say, to get that single foraminifera analysis, but something a little bit bigger that's still smaller and playing with getting really precise volume match and kind of letting them bleed out at the same rate and trying to get smaller samples that way. There are enough people now wanting to make this measurement and other mass spec companies that have gotten involved that we're starting to benefit from actual good old capitalistic competition. So as Thermo was kind of the first company to make a machine that could measure this, as other mass spec companies wanted to get in the game, people started adjusting and introducing new innovations from the hardware side that may help with some of this. So I'll talk about the mass spec we have at CU Boulder, which is one of the newer Thermo instruments, where they've made a bunch of changes to help get to smaller sample sizes. And in our lab, I literally got these text messages yesterday. I think we can comfortably measure, still using the bellows, at about 1.5 to 2 milligrams instead of 8 to 10, which is phenomenal for me. So I'm super excited about that. And playing with other kinds of things. So you can do things like play with all of your tuning parameters. So when they gave you guys the mass spec lecture, they show you all the different tuning parameters you can play with, both on the source end, sort of for getting your beam into the right place with the right intensity. So you can play with a lot of those parameters. And one of the things my lab manager has been doing while I've been gone is making a series of maps where you can adjust all those tuning parameters, where you exploit the tuning parameters to give you maximum sensitivity, so as much signal for your available gas as possible, versus where you might tune the machine to get your very best peak shape and precision. And somewhere in there is a sweet spot where you can kind of bump up your sensitivity as much as you possibly can, sort of at the limits of the precision that you actually need. And so that's been another part of getting the precision in our lab. Okay, so those are just examples of current challenges and opportunities, and there's a lot of different features both on the hardware and analytical side to work with. as well as sort of thinking about modern systems, which I'll talk about in a minute. OK. So I've talked about this mostly in the context of carbonate clumping, but it's really just the tip of the iceberg. So again, if we kind of think about where stable isotope geochemistry and now ecology started, we started with thermometry, an attempt to get temperatures out of carbonates. So there's kind of a sense of isotopic deja vu here. It was still something we really wanted the answer to, and so developing the clumped temperature system first was sort of the low-hanging fruit. But a number of different labs are moving into different molecules and exploiting a lot of the geochemistry in those systems. So this is all really, as Naomi already said tomorrow, this is all really at the forefront. And so if you're looking at some of these things and being like, well, that's great, but I'm not a geologist, I'm an ecologist, you're here because there was a geologist who said, well, we can reconstruct paleotemperature, right? And eventually, a lot of the other tools that burgeoned from that have expanded to ecology, archaeology, and a number of different things. So use your imagination about how some of these systems and these behaviors might be exploitable. OK, so there was recently, this is a figure from Ben Passey's 2015 sort of news and views perspective on 2 papers that came out simultaneously in Science in 2015, one that came out of Shuhei Ono's group, so this is the Wang et al. 2015 paper, and a paper by Lawrence Young and others, 2015. So these folks are working on methane clumping, and these folks are working on O2 clumping. And so what you see in this plot is essentially a sort of cartoon of different behaviors that you might expect, whether you're talking about 2 oxygen 18s in an O2 molecule, or whether you're talking about a C13 deuterium sort of clump within a methane molecule. And basically showing you can imagine that for both of those sets of clumps, you're going to end up with some equilibrium system. That's what's represented here, and strongly driven by temperature. And when we think about that, there's papers published looking at different settings of methane clumping and what that might show you about natural gas systems, where some of that methane is being produced in terms of natural gas production, which is certainly something the oil interested is interested. But you can also look at things. So this is a process clearly coming off of the equilibrium line. So here we have examples of microbial methane. So looking at a disequilibrium system, so here's a biologically driven system that creates its own fingerprint that you could see in sort of clumped isotope space. Right? So already you can kind of see that there's a number of different potential pathways, both from thinking about things that might be biological or introducing some other kinds of kinetic fractionations. And it introduces another term that we didn't explore. And in the interest of time, I won't have you do as an anti-clumping exercise. But if you take a look at our stochastic distribution of mass 47, just by chance, in an equilibrium system, we did end up with at least one clumped molecule. And we even had one of these weirdo other multiply substituted molecules, right? And anti-clumping, so if that's our stochastic distribution, and thermodynamics is sort of weighting chance in the sense of how you'd think about having weighted dice to try and help you get snake eyes. That's what they're kind of showing here. You can imagine that there are some biological or other kinds of processes that actually work to anti-clump things. So they're basically taking this and saying, you have some pool of rare heavy isotopes. You have the potential, just from chance, that you'd expect to end up, even though they're rare abundance, with some of these multiply substituted molecules. Anti-clumps is basically saying you end up finding some system works to distribute your isotopes in almost a more orderly fashion to get away from some of these clumps. So you end up with systems here, this sort of anti-clumped realm, which happens apparently as a process in photosynthesis within the clumping system of O2, but also in serpentinization-associated reactions associated with microbial gas, where they're actually probably being really choosy about where they're putting their heavy isotopes. And in the cases of the biologic systems, have some reason for why they want to be putting heavy isotopes where they are. And so you end up with even less clumps than you would predict just based on random chance alone. So again, this is kind of the frontier. There's a lot of different things going on in position-specific isotopes and looking at some of those molecules and what kind of information that would lead to. Any questions on some of that? As Naomi already said, and I kind of made a recommendation a little bit later on, but she posted John Eiler's 2014 Frontiers in Stable Isotope Geoscience. If you're interested in any of the prospects for what's going on outside of just the clumped isotope thermometry side of this, the carbonate clumped isotope thermometry, definitely check out that paper. So they go through a lot of the different, and kind of foreshadow the different directions they're trying to push things in. Cool. Okay, so do people, and I guess I'll finish up here and then give people a quick 5-minute shake your head and wake up. The key here, and just in terms of thinking about the broader stable isotope geochemistry of isotopologs, is that whatever you're trying to do with some of these things, in the same way that we think about all of the different things we can measure at once, is it's just giving you more variables to play with that are intimately tied to the same sample. So if you go back to this image, you can imagine in 3-dimensional space, you might be able to make, with methane, here you have your clumping plot, but you could also have in 3-dimensional space your sort of delta D versus delta 13C bivariate plots. You guys are really used to now looking at bivariate plots of sort of complementary isotope systems. So now start thinking in 3 dimensions or 4 dimensions, which our brains start having trouble with. But it's just giving you a lot more information from exactly the same samples to play with, and a better chance that things that you may see, say, in bivariate space, where you can't quite tease apart, I can't quite say methanogenesis is happening in this setting and that it's not something else, just as an example. Here you would end up having that additional space to sort of see how your populations fall out differently and actually parse apart different processes.